Welcome. In today's video, we're going to be discussing hypothesis tests for a single mean mu. So if we're wanting to test a single population mean, again, the notation for that is mu, mean, average, whatever it might be. So the situation we're going to be dealing with today is analogous to what we looked at when we were dealing with 8.2, and we were looking at confidence intervals for a single population mean. So in that section, we discussed the validity of the test procedure rests on the assumption that the population distribution is at least approximately normal. Now, in this case, we want to consider hypotheses of the form, our null being that mu is equal to mu naught or mu sub 0, and then our alternative h sub 1 is that mu is not equal to mu naught or mu sub 0. Then we have the following test statistic: x bar minus mu naught divided by s over the square root of n. If the null hypothesis is true, this test statistic has a t-distribution, and you may recall that the t-distribution, the parameter it depends on is the degrees of freedom. In this case, it would be n minus 1. So whatever our sample size is, minus 1. Now, when we're doing a hypothesis test on a mean, or any type of hypothesis test, we need to know how are we going to calculate our p-values. How are we going to calculate this item at the end that's actually going to drive our decision, whether we reject or do not reject the null hypothesis? We know the distribution of our test statistic when h sub 0 is true. That is the entire basis for the logic, the decision-making process that we go through when we do a hypothesis test. Oftentimes, this may be referred to as the reference distribution or the null distribution. And then based off of that, we can calculate our p-values. So here we're going to let T naught be the calculated value of our test statistic. So if we are conducting a two-tailed test. Now you may ask, what is a two-tailed test? Recall, a two-tailed test is when we have a not equal to alternative hypothesis. So going back to, and this would have been the situation we looked at on the previous slide, when our alternative hypothesis is not equal to. So we could have mu not equal to mu naught. Now then, if that is our situation, the whole reason it's called a two-tailed test or a two-sided test, a couple of reasons. One, you can get it from the alternative hypothesis itself, because we're going to be rejecting the null in favor of the alternative if we get evidence that mu is greater than or less than mu naught. So in either of two directions. Now, practically, when we're actually going to find the p-value, what that means is we want the probability in both tails. So if we marked off, and remember, T naught being our test statistic value that we've calculated, so we've plugged the numbers in to the formula. If we mark off the positive and the negative value of that, then we want the area in both of those tails. That's going to be our p-value. Now, one thing that's nice dealing with the t-distribution, and this will be true with the normal distribution as well, it is symmetric. So what that means is, the upshot of that is that we can just find the probability of our random variable capital T being in one of those tails and then multiply it by 2, which is what the formula down at the bottom is stating. So it's saying, okay, we can find this area over in the right, and then we can just multiply that by 2. Try to get that a little, hey, there we go. So now let's move on to the one-sided or one-tailed versions. Now notice we have two different versions here. So the first one we have a right-tailed test. Now, with a right-tailed test, that means that our alternative hypothesis is going to be greater than. So we could have, just speaking very general here, we could have that mu is greater than mu naught. And something I'll point out, obviously we're discussing this in terms of a single mean mu. This right tail, what we're going to discuss in a moment, left tail, two tail, all of this applies to other parameters as well. So we could be talking about P, the population proportion. We could be talking about the difference between two means. Any of those things, all of this is still going to be consistent. So if our alternative is greater than, then that means we have a right-tailed test. So our p-value, we would mark off the value of our test statistic and then find the area to the right of that. That's going to be our p-value. Now, you can see here it's given the tail over on the right. That doesn't have to be the case. Most of the time it will be, but it is possible that we could be taking a right-tailed test. Unlikely, but it is possible that we could get a t not a test statistic value over on the left. And if we did, our p-value would still be the entire area to the right. Again, that's unusual, but not impossible by any stretch of the imagination. Now then, our last scenario, which you can probably reason by deduction. If we're talking about a left-tailed test, then that means our alternative hypothesis is less than. So we'd have it of the form, we could have mu less than mu naught. A less than test. So to find our p-value, we would again, it's analogous to what we just talked about a moment ago. We would mark off our test statistic value, t sub 0, and then find the area to the left of that, less than that value. Again, less than is a left-tailed test. You can remember the L's go together. Less than, left-tailed. A greater than test is a right-tailed test. Great, you got the second letter there is R. That can help you remember that it is a right-tailed test. All right, so for example, if we're actually going to be looking at one of these, so suppose we are conducting a right-tailed test with 14 degrees of freedom. So 14 degrees of freedom, that would have meant, if you're working backwards, that our sample size would have been 15. So the row in our t-table that corresponds to 14 degrees of freedom is given here on the slide. So suppose our test statistic value is calculated to be 2.8. Well, what would be the p-value for this test? Now remember, the way the table is set up, it gives us the right tail. So that makes things a little bit simpler on us since we're doing a right-tailed test, which would mean our alternative hypothesis would be greater than. So how would we find our p-value? Well, we'd want to find 2.8 in the table. So if we look at that top row, we're going to see, okay, we don't have 2.8 exactly, but it's going to be somewhere between 2.624 and 2.977. Now, we need to find the p-value, so we need to know the area to the right of 2.8. Well, we know the area to the right of 2.624 is 1%. The area to the right of 2.977 is 0.5%. So while we don't know exactly what the area to the right of 2.8 is, we do know that it's going to be somewhere between 1% and 0.5%. So it's going to be somewhere between 0.01 and 0.005. So if we wanted to write that out, we could say point, and that's supposed to be a decimal. Let's try and get an actual dot. Hey, there we go, that'll work. So 0.005 is less than our p-value, which is less than 0.01. So again, we don't have the exact value of our p-value, but we do have a range that we know our p-value is going to fall into. A couple of small notes about this. One, anytime you're talking about a p-value, make sure you actually write p-value. Sometimes there's a urge to just, shorten it and just write p. The problem with that is p stands for something completely different when you're talking about statistics. That stands for the population proportion. So we don't want to get our notation confused. So whenever you're talking about a p-value, make sure you actually write p-value. Secondly, while we found the p-value to be within a range based off of our table, that doesn't mean it's impossible to find the exact p-value. That's not true at all. You could use any type of technology to calculate, okay, if I've got 14 degrees of freedom, so I've got a t-distribution with 14 degrees of freedom, and then I want to know the area to the right of 2.8. Well, we can use, your calculator. If you've got like a graphing calculator, it likely has a statistics package that you could calculate this in. You could just Google t-distribution calculator and find many of them on the internet. You can calculate it in R, you can calculate it in Excel, yada, yada, yada. The list would go on. But in terms of using the table in the book, we'd know it would fall in this range. All right, so now what we're actually going to look at is doing an example. So suppose that we are testing the hypotheses mu equal to 17 versus mu not equal to 17. And we had a sample of 16 observations, and that sample gave us a sample mean of 20 with a standard deviation of 7. So once we have our hypotheses, the next step that we want to do is actually calculate our test statistic value. So here we've got our test statistic formula. T naught is equal to x bar minus mu naught divided by s over the square root of n. One small note on the notation. So here you'll see that it's written with a capital T. Typically in statistics, the reason for that is if you have a capital letter, then that's referring to the random variable. And then if you have a lowercase letter, that's referring to an actual value of that random variable. So you may recall a few slides ago when we were talking about various values of our test statistic, it was lowercase t sub 0. That's the reason, because we're actually talking about a value at that point. So if I were actually going to calculate this, so I would have t sub 0 is equal to, and then x bar, that's our sample mean. Here we're told that that is 20, minus the value we're testing against, minus mu naught. Mu naught, or when you get to doing other types of hypothesis tests, it might be p naught or whatever. That's always the value that we're testing against. It's the value that comes from our hypotheses. So in this case, that's going to be 17 divided by s over the square root of n, s being our sample standard deviation, which here we're given that as 7, and then divided by the square root of our sample size, which is 16. And then we can calculate our test statistic value. Plug and chug, we should end up getting 1.71. All right. So now that we have our test statistic value, we need to find our p-value. So if we were to look at this, if we were to actually draw our distribution. So, and I'm sure this isn't going to look all that pretty, but we're going to go with it. It's not too bad. I'll take it, actually. So, we draw our t distribution. Now, this is going to be a t distribution with n minus 1 degrees of freedom, so 15 degrees of freedom. Now, to find our p-value, we need to mark off our test statistic, which is 1.71. And I guess just to complete this, I usually like to mark off the mean, which is 0. And so over here somewhere on the right, I'm going to have 1.71. And then we're going to want to find the area in that tail. Now, since we're dealing with a two-tailed test, we also would want to mark off the negative of our test statistic. So in this case, negative 1.71. And look at the area in the left tail as well. So the area in both of those tails added together would be our p-value. So again, going through and calculating our test statistic, we should get a value of 1.71. And then if we go through and look up 1.71 in our table, so if you go to your t distribution table with 15 degrees of freedom, you'll see that the area to the right of 1.71 is something between 0.05 and 0.025. So that means this area, whatever it is, it's going to be, let's see, at minimum 0.025, at maximum 0.05. So that area is going to fall somewhere in that range. Same thing could be said about the left tail. And then if we want to find our p-value, we want the area in both tails combined. So to get the area in both tails combined, we could just multiply this by 2. So this is telling us that our p-value is going to be somewhere between, well, double these, so somewhere between 0.05 and 0.1. If our alpha is 5%, so alpha is 0.05, then if our p-value is somewhere between 0.05 and 0.1, obviously our p-value is greater than alpha. If we have a large p-value, then our decision rule is always to not reject the null hypothesis, or sometimes that's termed as fail to reject the null hypothesis. All right. Thank you very much, and that will conclude our video discussing hypothesis tests for a single mean mu.